Hello, all of you. Let's start this session with the topic as operational amplifier as a differentiator. Okay, a differentiator means something that enables a difference to be made. Here, operational amplifier, when acts as a differential amplifier, it produces actually an output voltage proportional to the rate of change of applied input voltage. Actually, an output voltage amplitude is directly proportional to the rate of change of applied input voltages. And again, with the active component like operational amplifier, here it is called as active differentiator. It is an inverting operational amplifier configuration. Again, in the circuit of differential amplifier, capacitor is used in series connection with the input voltage. So this becomes a high pass filter. High pass filter means which passes the high frequencies and blocks all other frequencies from the circuit. Usually, these circuits respond to triangular and rectangular input waveforms. The circuit diagram for operational amplifier as differentiator looks like this. Here we can see the capacitor C1 is connected to input voltage V in. An inverting op amp is used again. Capacitor C1 and resistor RF is the feedback circuitry. That is, RF is the feedback resistance here. R comp means compensation resistor is at non-inverting terminal. X point is at negative and Y point is at positive terminal, and V out is the output voltage. When the applied input voltage is positive going, you can see the current I and direction of that current I. This current I shown in the diagram flows through the capacitor C1. When the applied input voltage is positive going, the current I flows through the capacitor C1. And as an op amp internal flowing current is 0, all this current I flows through the resistance RF. Here, output voltage becomes V out is equal to minus of I into RF. Minus because input is provided to the negative terminal of op amp. Here, I into RF is nothing but the input voltage V in. So we can say here as output voltage is directly proportional to the rate of change of input voltage. Now notice the points X and Y. X is at virtual ground. Now what is virtual ground? For this, please see my video on virtual ground in the playlist of analog electronics. Again, because of this virtual ground potential, Vx is equal to Vy and they are all equal to 0. That is, we can write Vx is equal to Vy equal to 0. Observe the input side in this diagram where V in, C1 and Vx points are there. Then the current I can be given as I is equal to C1 into bracket d of V in minus Vx by dt. As Vx is equal to 0, this equation becomes I is equal to C1 into dV in by dt. And now from the output side, the current I can be given as minus of V out minus Vx divided by Rf. Again, Vx is equal to 0, therefore minus V out divided by Rf. The output side current I is equal to what? Minus V out divided by Rf. Now, let's equate above two equations of current from RHS and it becomes C1 into bracket dV dv by dt is equal to minus Vout divided by Rf. Therefore, for Vout, for output voltage, we can write Vout is equal to minus C1 into Rf into bracket dV in by dt. This equation again indicates that the output Vout is C1 Rf times the differentiation of the input voltage. That is, output voltage is nothing but the product of C1 Rf and the rate of change of input voltage. Here, R1CF is also called as RC time constant of the differentiator circuit. Again, the negative sign indicates that output is out of phase by 180 degree with input. Here, the main advantage of the active differentiator is its small time constant RC, which makes the differentiation. Observe this input-output waveforms actually. For a step input voltage Vm, which is applied to op-amp as differentiator's input, mathematically it can be expressed as Vout is equal to minus C1Rf into dVm by dt. For simplicity, assume the product C1Rf equal to 1, that is unity, and as Vm is constant, Vout equal to 0. But practically this output is not 0. The step input waveform takes a finite amount of time to rise from 0 volt to Vm volts, you can see in this diagram. Okay. Again, for the square wave input, when this square wave input is applied to the differentiator amplifier, the output becomes as positive and negative spikes corresponding to the charging and discharging of capacitor. You can see and observe the diagram here. Again, for sine wave as an input to differentiator, we know the equation of sine wave is V of t is equal to Vm sin omega t. Let's take Vout equal to minus C1Rf into bracket dVm sin omega t divided by dt or by dt. For our convenience, suppose C1Rf equal to 1 or unity, then Vout becomes Vout equal to minus Vm into omega into cos omega t. The differentiation of sine is cos. Here, for sine wave input, differentiator output is cosine wave, and observe the input output waveform here. Now let's see the actual or practical op-amp circuit as a differentiator. Again, it actually acts as a high pass filter. Here in this circuit, R1 is connected in series with the input capacitor C1 and capacitor CF is connected parallelly with feedback resistor RF. This combination of components in this circuit avoids the noise. The output voltage of this practical op-amp as differentiator amplifier is same as V out is equal to minus Rf into C1 into dV in by dt. That is V out is Rf C1 times the differentiator input or differentiation of the inputs. But R1 and CF stabilizes the circuit at higher frequencies and also reduces the effect of noise on the circuit. Applications of op-amp as differentiator. Commonly, this circuit is used in wave shaping circuits to detect high frequency components in the input signal and to operate on a triangular and rectangular signals actually. Let's overlook the summary of op-amp as a differentiator. An op-amp differentiating Amplifier is an inverting amplifier circuit configuration which uses reactive components, usually a capacitor than inductor. The differentiator performs mathematical differentiation operation on the input signal with respect to time. That is, output voltage is proportional to the rate of change of input signal. Differentiating circuits are commonly used to operate triangular and rectangular signals. While operating on sine wave inputs, differentiating circuits have frequency limitations. I hope you have understood operational amplifier as a differentiator. If any doubt, please comment me on this video's comment section. Thank you.